Well, hello and welcome. We are beginning activity 21, and none other than lesson 21-1. And we've been focusing for the last few activities primarily on the right triangle, which, if we recall, a right triangle is a triangle with one right angle. And so now in activity 21, we're going to turn our attention to some special right triangles. There are two very special right triangles that we actually hinge a lot of trigonometry on later on in geometry. These two very special right triangles, and I'll go ahead and give it away. The first one is known as the 45-45-90 triangle. And of course, we are referring to 45 degree, 90 degree. We're talking about the angles of this special right triangle. So let's take a look at our learning targets. Our first learning target, we are going to describe the relationships among the side lengths of a 45-45-90 triangle. There's some special relationships that always occur, and we've been studying similar triangles. So if any triangle has angle measures 45, 45, and 90, there's some relationship we can establish that all 45, 45, 90 triangles will have because, right, angle similarity. Once we describe those relationships, we will then apply those relationships in special right triangles to solve problems. So once we figure out what the relationship is, we're going to start solving problems, for the most part, finding missing sides of these special right triangles. So without further ado, if you would draw a line below 1C, we're going to chunk item 1A through C together. So go and pause the video, read the text here, a unique idea, before playing through. So an interesting idea here to learn the first special right triangle, we're talking about quilts. And a lot of quilts are, as it's stated here in our text, they're often made of squares, and often those squares contain certain patterns. And we're looking at the friendship star here. So number one, the friendship star quilt contains 5 small squares. And I want to reiterate that we are dealing with squares, and the 5 small squares we're talking about are this one, the one in the middle, and these 2. And 8 triangles, and hopefully you can observe that here. You might have only seen 4, the ones with the actual pattern, but the ones without the pattern are also triangles as well. So there are 5 small squares and 8 triangles. And I identified the congruent figures, and I said the larger square that's divided into 9 smaller congruent squares. So we had this original block here, and it was divided into 9 small squares that are all congruent to each other. And then 4 smaller squares were divided along their diagonals. Remember, a diagonal is what connects opposite angles of a quadrilateral. So this square right here was divided along its diagonal to create 2 congruent triangles. Therefore, there's actually 8 congruent triangles in this pattern. And they ask us to dive a little bit deeper into these triangles and what's unique about these triangles. In B, it says classify the triangles in the quilt block by their angle measures. And so if we started with the square, which has 4 90-degree angles, and then we divided that square across the diagonal, we now have right triangles because the square had right angles, and when we divide it along the diagonal, we now have right triangles. And then it said classify the triangles in the quilt block by their side lengths. Now you might be wondering, how can we possibly know what their side lengths are? Well, it all goes back to the fact that we are dividing up squares. Sorry about that. But anyway, we are dealing with the square. And what makes a square so unique is that it has 4 congruent sides and 4 right angles. And so we already established that we're dealing with right triangles here. But now focus in on this right triangle, this one in particular. Notice that we know for a fact that 2 of its sides are going to be congruent. Therefore, we are dealing with an isosceles triangle. So I actually wrote what we're dealing with in total with these two ideas combined, a right isosceles triangle, which is a triangle with one right angle and two congruent legs. Remember, in a right triangle, the two sides that create the right angle are referred to as legs, and the side opposite of the right angle, typically our longest side, is referred to as the hypotenuse. So just keep that in mind if you're wondering. We're going to get specific and use the term legs a lot more often than we use sides. So the last thing they wanted us to do is says figure out the measures of the acute angles in each of the triangles. And I wanted to approach this one a little bit differently or together and recall the three angles of any triangle. It's actually called the triangle sum theorem. So any triangle in the world, the three angles have to add to equal 180 degrees. So A plus B plus C is 180 degrees. Well, since we are dealing with a right triangle, we know that one of its angles is already 90 degrees. So between the other two angles, these two angles, A and B, have to sum to equal 90. Well, if we are dealing with an isosceles triangle, if two of its legs are congruent, then two of its angles are congruent. Well, think about it. There can't be another 90-degree angle because the three angles of any triangle has to add to equal 180. So these two angles, A and B, actually have to be equal to each other. So if A and B has to add to equal 90, in other words, they are complementary angles, we can take 90 and divide it by 2 to find out the degrees of both of these other acute angles. And what are those measures? 45 and 45. Hence, we are discovering the 45-45 90-degree triangle. So a right isosceles triangle is known as the 45-45 90-degree triangle. So if we refer to it as right isosceles or as the 45-45 90, we're talking about the same triangle. So now let's kind of use this idea that we know that two of its legs have to be congruent. Let's see if we can uncover a unique relationship with this. So it says the Hoover High Student Council decided to make friendship star quilts of various sizes with different size quilt blocks. We are going to use the Pythagorean theorem, which we learned in activity 20 or remembered in activity 20, to find the exact values. That means we're not going to round here. We're going to find the exact values of the missing dimensions and ratios in the table below. Recall, we really talked about ratios when we were dealing with similar triangles because similar triangles have corresponding sides that are proportional, and proportional means it has ratios that are equal. So we're eventually going to figure out the ratio of the hypotenuse of any 45-45 90 triangle compared to the leg of any 45-45 90-degree triangle and see if there is a common ratio that we can use to then solve problems. So we're going to chunk item 2 by itself. So work item 2 before playing through the video. Okay, hopefully as you were working through this using the Pythagorean theorem, and a lot of that work is over here on the left-hand side, you figured out that there's a pattern emerging. Okay, there's a ratio that is consistent between the hypotenuse and leg of any isosceles right triangle. Now, you might have been confused here, but we started with a 9x9 block, and then each of the squares, the smaller squares, will have a 3-inch leg, just like we saw in the original design. So 9x9, each of the smaller squares will then have a side length of 3. So that's what you're wondering here. So I wouldn't really get hung up on this aspect here. Obviously, we're just using the quilt block to help us uncover the ratio. But here, the length of the triangle leg is 3 units or 3 inches. And so if we have 2 legs that are congruent, we're going to use A and B, and they're going to be the same value of 3. So 3 squared plus 3 squared equals C squared. 3 squared is 9, so 9 plus 9 is 18. Then to find C, we take the square root of both sides. And this is where they wanted us to write it in an exact value. You know, 18 is not a perfect square. When you put square root of 18 in the calculator, you do get a decimal. So one method I chose to simplify square root of 18 was rewrite 18 as two factors multiplying, in which case one of them is a perfect square, in this case 9. So it would be square root of 9 times 2. Well, 9 being a perfect square of 3, we take the square root of 9 and put 3 outside the square root because it's a perfect square. And 2, not being a perfect square, we leave inside the square root and we have 3 times the square root of 2. In fact, I challenge you here, if you put square root of 18 and 3 times the square root of 2 in the calculator, you get the same decimal. These are the exact same number. This is just a simplified form of that. The same way if we put 2/4 in the calculator, we get the exact same decimal as 1/2. They're the exact same number. This is just a simplified version of this, just like 1/2 is a simplified version of 2/4. So we got 3 times the square root of 2, and then they wanted to write a ratio of the hypotenuse to leg. So this is one way to write a ratio. We typically write a fraction, but so the hypotenuse length was 3 times the square root of 2, and the length of the leg was just 3. So then we move on to the 15 by 15, which means we have a length of the triangle leg 5 inches. So A and B in our Pythagorean theorem will both be 5. So we did 5 squared plus 5 squared equals c squared. Of course, 5 squared is 25. 25 plus 25 is 50. And to get rid of c squared, we take the square root of both sides, and we get the square root of 50. Maybe go ahead and put square root of 50 in the calculator, just see what you get as a decimal. Because when we start simplifying it, we rewrote 50 as 25, a perfect square, times 2. Notice 2 keeps popping up here. There's a reason for that. So we take the square root of 25 and get 5. Notice we put it outside of the square root because it's a perfect square. And then 2, being a non-perfect square, we leave under the square root. So square root of 50 is 5 times the square root of 2. And if you put both of these in the calculator, you should get the same decimal. And so we wrote the ratio again. The hypotenuse was 5 times the square root of 2, and the leg was just 5. And so if you're not developing or noticing a pattern, let's look again at 3, or C is what I called it, where each leg was 1 unit in, or 1 inch in length. So 1 squared plus 1 squared equals c squared. 1 squared is 1, not 2. A lot of times we get that mixed up there. It's 1 times 1. 1 plus 1 is 2. And the square root of 2, just like we said back here, is not a perfect square. That's in simplified form. So on this third section, we see that the ratio of the hypotenuse to a leg is square root of 2 to 1. In other words, whatever the length of our leg is, we multiply it by the square root of 2, and that's our hypotenuse. Go back to the other two. The length of our leg was 5. To find our hypotenuse, we multiplied it by square root of 2. In the first one, we saw that the length of the leg was 3. To find the hypotenuse, we multiplied by the square root of 2. And we see that pattern again here. I would imagine most of us skipped the 1.5 because it was maybe a little bit more challenging with the decimal. But we see the pattern again. The length of the leg is 2. The length of the hypotenuse is 2 times the square root of 2. So with that pattern, let's see if we can go and figure out the rest of this table. So if the length of the leg was 1.5, we're multiplying it by 3 because it's a 3 by 3 square. So it'd be 4.5 by 4.5. And if, for example, the length of the leg was 5, now the hypotenuse 5 times the square root of 2. If the length of the leg is 1.5, it will be 1.5 times the square root of 2. And so the ratio will be 1.5 times the square root of 2 to 1.5. Now, they're just trying to really see if you're paying attention to the relationship that's evolving here. So if the length of the leg was 2 and the length of the hypotenuse was 2 times the square root of 2, then what will be the length of the leg here if they give us the hypotenuse? Well, if the idea is we take the length of the leg and multiply it by the square root of 2, this value in front of the square root of 2 is the length of the leg. So the length of the leg will be 6. And therefore, the dimensions for our quilt block will be 18 by 18. And of course, we'll write the ratio 6 times the square root of 2 to 6. Now, this last one's a little bit tricky because if you notice, we don't easily see what we multiplied by square root of 2 to get 4. So this is actually I'm going to use this as an opportunity to show you how we're going to start approaching solving problems using this relationship that's forming where we take the length of the leg and multiply it by the square root of 2. So if 4 is our hypotenuse, and we should be able to take the length of the leg and times it by the square root of 2, well, to find the leg, we should be able to do the opposite, divide by the square root of 2. And that's the math that I'm going to show you here, where we're going to take 4 and divide it by the square root of 2. You will notice that it'll, of course, cancel out over here. As crazy as it is, just like regular math that you've learned, when you divide by what you were multiplying, it cancels out. Now, if you put 4 divided by the square root of 2 in the calculator, you get a decimal. And obviously, we're trying to avoid decimals here. So let me show you how to divide by the square root of 2. There's actually no division at all. It's actually multiplication. So let's look at this fraction, 4 divided by the square root of 2. It is considered irrational to have a square root in the denominator of a fraction. So to resolve that, we're going to multiply by itself, aka squaring it. That's how you get rid of a square root, is you multiply by itself. So we're going to multiply square root of 2 times itself, square root of 2. And whatever you do to the bottom of a fraction, you have to do the same to the top. So I'm going to multiply the top by the square root of 2 as well. You might have thought maybe I should multiply it by 4. No, whatever you multiply the bottom by, you have to multiply by the top as well. So square root of 2 times itself is the square root of 4, which is 2. And 4 being a non-square root and 2 being a square root, we just simply multiply them by saying 4 times the square root of 2, which would be this. So now we have 4 times the square root of 2 over 2. Another way to rewrite this is 4 over 2 times the square root of 2. And when we write it this way, we see that 4 can actually divide by 2, and we get 2 times the square root of 2. So we're actually going to use this math, given the hypotenuse, to find the length of the leg. So the length of our leg is 2 times the square root of 2, which is a little bit more challenging. It's interesting that they decided to put that here in this table as you're discovering the relationship, but it's a challenge that we're up for, and we're going to use that to solve missing legs later on. So our ratio will be 4, 2 times the square root of 2. And if it's a 3 by 3 block, it should be 6 times the square root of 2 inches by 6 times the square root of 2 inches. In other words, 3 of these legs together. And all I did was do 3 times 2 to get 6 times the square root of 2. So now we're going to really figure out, we've kind of mentioned it as we went through the table, but really figure out the pattern that's occurring in this table and make a very general statement about finding the length of legs or the hypotenuse in this special right triangle. So we're going to chunk items 3 and 4 together. So go and pause the video, complete item 3 and 4 before playing through. Okay, so item 3, they wanted to know what pattern did we notice. Now, we could really focus in here on talking about the ratios, and that's really how we figured this out. The ratios are leading us to believe that the length of the leg times the square root of 2 is the length of the hypotenuse. So that's really the pattern I wanted to stress here, is that the length of the leg times the square root of 2 is the length of the hypotenuse. Therefore, think about it the other way. The length of the hypotenuse divided by the square root of 2 is the length of the leg. And so we're really trying to come up with a way, obviously, to solve problems based on this special pattern that's emerging in the 45, 45, 90 triangle. So suppose you're only given the length of one leg of an isosceles right triangle, write a verbal rule for finding the lengths of the other 2 sides. Well, in an isosceles right triangle, the 2 legs must be congruent. So there's one of the other sides. And the hypotenuse is the length of one of those legs times the square root of 2. So if I can tell you one leg of an isosceles right triangle, draw one real quick. If I tell you one leg of an isosceles right triangle, you know that the length of the other leg is the same measure, and then the hypotenuse is the length of the leg times the square root of 2. And so notice they wanted us to do that kind of idea here and just prove it using the Pythagorean theorem, using L for leg and H for hypotenuse. So if the two legs are in fact congruent, we'll use L for both A and B in the Pythagorean theorem, and we'll use H for the hypotenuse. So we'll do L squared plus L squared, and notice it's the same pattern we were doing in the table to find the length of our hypotenuse. L squared plus L squared. We can combine these two because they are like terms. Remember, if it's the same variable raised to the same power, you can add them together. And so 1L squared plus 1L squared is in fact 2L squared. And to get rid of, we want to know what H is, not H squared, we take the square root of both sides. So the square root of H squared is H, and then let's tackle the square root of 2 times L squared. Well, L squared is a perfect square of L. So we take the square root of L squared and we get L, and the square root of 2, not being a perfect square, stays underneath the square root, just like we said over here. Square root of 8 we rewrote as a perfect square 4 times a non-perfect square 2. And we took the square root of 4 and we got 2. And because 2 is not a perfect square, we left it underneath the square root. Same idea here. L squared was a perfect square. So we took the square root of L squared and got L, put it outside the square root. 2 was a non-perfect square, so we left it underneath the square root. So what we're saying here, very similar to what is drawn here, is that the length of the hypotenuse is the length of the leg times the square root of 2. So we can use this now to solve problems on the Check Your Understanding. So this is a great opportunity to see if we can apply what we just learned. If you notice, we're hardly given any information on these diagrams. You know, we were taught with the Pythagorean theorem, if we knew 2 sides of a triangle, then we could find the third using a squared plus b squared equals c squared. Well, the reason that's a challenge here is because if you notice on item 5, we're actually only given the length of the hypotenuse. We don't have 2 sides. So this is where the 45, 45, 90 relationship really comes in handy that we said on item 4. So if you would, complete all the way to item 9. So we're going to chunk it. Obviously, do the work out here in the My Notes section, but try it before playing through the video. Now, there was potentially some math that might have been a little bit confusing to you. I'm going to explain those things, but overall, if we can learn this relationship, it makes this math so quick for us. So for item 5, we're asked to find x, which is the length of one of our legs. Remember, the legs are the 2 sides that make the right angle. So we are finding x, or we could call it L if we want to. And we are given the hypotenuse, which in this case is 17. So 17 is the hypotenuse. X is our leg. So the relationship we learned in item 4 was the hypotenuse is equal to the length of the leg times the square root of 2. So I'm going to replace h with 17, and our task is to find the length of the leg, which in this case they called x, but we can call it L. So if I'm trying to find L is multiplying by the square root of 2. So to get rid of the square root of 2, we divide both sides by the square root of 2. And notice it canceled out here. But as we mentioned, we can't divide 17 by the square root of 2. They're actually considered unlike terms, and we'll talk about that a little bit more on item 6. So we have to do this process to divide by the square root of 2, or in other words, rationalize the denominator by multiplying the top and bottom of this fraction, that's what it is, by something that gets rid of the square root of 2. So the idea here is we are taking the square root of 2 and squaring it, multiplying it by itself so that we get rid of the radical in the denominator. Look here, square root of 2 times square root of 2 is the square root of 4, which is 2. So that's why we multiplied square root of 2 times itself to get rid of that square root. Well, whatever we did to the bottom, we had to do to the top. So we get 17 times the square root of 2. We can't actually multiply those. They're considered unlike terms, if you will. Just like when you multiply 3 times x, you get 3x. Here we have 17 times the square root of 2, and we get 17 times the square root of 2. You'll notice that variables act a lot like square roots. Now, I actually wrote this a little bit differently because a lot of us were getting comfortable with this idea. You know, a number times a square root, But when it was a fraction, we get, kind of caught off guard. It seems a little bit more intense. But 17 times the square root of 2 divided by 2 is the same as 17 over 2 times the square root of 2. So just a fraction times the square root of 2. Or you can simplify 17 over 2 to 8.5 times the square root of 2. Now, item 6, we're obviously given some different information. We are asked to find the hypotenuse, and we are given the length of a leg. In this case, the length of the leg is 4 times the square root of 5. So again, let's use that relationship. The hypotenuse is the length of the leg times the square root of 2. And I'm going to replace L with the length of our leg, 4 times the square root of 5. And so the math you're going to see here is how very similar to the reason this works, we see something similar working here. So let me explain that math. So let's suppose we have some square root with it's actually called a coefficient, a number in front of it. So a times the square root of b, and we're tasked to multiply it by c times the square root of d. Well, we're really multiplying just like if we had 3x times 4x. We're multiplying what we consider in our mind like terms. In this case, we multiply 3 times 4 and get 12, and x times x and get x squared. We do the same thing with square roots. We'll multiply the a times c because they are both, if you want to say this, not under the square root. So we'll multiply a times c and get ac. Sorry about that. And we'll multiply b times d because they both are square roots, and we'll get square root of bd. So the idea here is when we multiply 4 times the square root of 5 times the square root of 2, we're going to multiply square root of 5 times the square root of 2. And 5 times 2, just like in regular mathematics that you learned in elementary school, is 10. So the length of our hypotenuse is 4 times the square root of 10. Okay, so we're seeing probably a couple mathematic principles that maybe we didn't learn in Algebra 1 or maybe in a previous math course, but we're really hinging on the ratio, the pattern, the relationship we learned in this lesson here. So again, we might be a little confused here, but we'll work on that. And even on 7, we might get confused with the math that's happening here, but we'll work on that. So they tell us in item 7, we're given the length of the hypotenuse, which is 5 times the square root of 12. And we're looking for the length of one of our legs, which we'll call L in this case. And so we know that the hypotenuse is the length of the leg times the square root of 2. So 5 times the square root of 12 is equal to the leg times the square root of 2. So if we're trying to find the length of the leg, we'll divide both sides by the square root of 2. Now, just like you can divide here, these two square roots, and in fact, they cancel because you're dividing by what you're multiplying by, we do something very similar over here. If you notice, we now have a square root in the numerator, and we have a square root in the denominator. And so the mathematic principle at play here is if you have a times the square root of b over the square root of d, you can actually, just like you can multiply b and d here, you can divide b and d here. So we'll write it as a times the square root of b over square root of d, or a times the square root of b over d. And so just like we see that math at play with multiplication, we can apply that same principle with division. And so to make this process a little easier, we can divide 12 and 2 because they're both square roots, just like we can multiply 5 and 2 here because they're both square roots, and 12 divided by 2 is 6. So the length of our leg is 5 times the square root of 6. Now you might be wondering, why wasn't it so easy back here? What created this whole process that potentially confused us? Well, if you notice in the numerator, we did not have a square root. We simply had 17. So we had to go through this process of multiplying top and bottom by the square root of 2 to rationalize the denominator, to get rid of the square root of 2 in the denominator. The reason it worked out so much easier here is because we had a square root in the numerator that we could divide by the square root of 2. Now, item 8, just taking this quilt block a little bit further, they want to know the dimensions of the smallest triangle on the 12 by 12 inch quilt block shown. So if this is 12 inches by 12 inches, then one of these squares, because there's 3 of them, one of these squares has to be 4 inches wide. And if it's cut in half, the length of the legs of our right triangles are 2. So we're asked to find the dimensions, in other words, the length of each side of the smallest triangle. So we have the two legs, which are both 2 inches in length. And we're establishing that the hypotenuse is the length of the leg times the square root of 2. Notice how easy this is if we know this pattern. We don't have to do the Pythagorean theorem here. The length of the leg is 2 in this case, so I'll replace L with 2. So right off the bat, we see the hypotenuse is 2 times the square root of 2. And here are dimensions, 2 times the square root of 2. And we probably should write inches. So notice how knowing this relationship in the 45, 45, 90 makes solving these problems much quicker. Is it doable with the Pythagorean theorem? Absolutely, because 2 of the legs are the same length. So you could do 2 squared plus 2 squared and find the length of your hypotenuse squared. The pattern just makes it a little bit quicker for us. Last but not least, item 9, the perimeter of a square, I think that's important to mention, is 40 centimeters. So the total distance around the square is 40, and if all 4 sides of a square are congruent, then we take 40 divided by 4, and we get 10 centimeters in for each side. And it asks us to find the length of a diagonal. Remember, a diagonal is a line or a segment that connects opposite angles. So you could have done this diagonal or the other one, really doesn't matter. And so we're actually finding the hypotenuse of an isosceles right triangle. So if we know the length of our legs is 10, we're trying to find the hypotenuse x. So if L is the length of our leg, which is 10, the hypotenuse is 10 times the square root of 2, in this case, centimeters. So notice we can really, if we remember the pattern, we can make solving for missing sides of these right triangles a lot quicker. That is the end of lesson 21-1, the 45, 45, 90 special right triangle. As always, go back to your learning targets, reevaluate your understanding. If you feel comfortable with those, if you feel really comfortable with this lesson, put a 5. If you still feel a little uneasy, put a 3. It just helps you gauge how well you're learning the material. And as always, complete the lesson practice following this page. Thank y'all for watching.